Okay, I'm ready. Yeah, thank you, Antonio. I am glad to be here today. First, I would like to thank the organizer for making possible this workshop and for the opportunity to share to you our recent work on undular bores, on weakly nonlinear water wave models, and on the free surface Euler equations. This is a joint work with Professor Noel Smythe that is around here, and you may know him very well, and with Professor Tim Marchand from the University of Melbourne. And this work has been done while I was a postdoctoral researcher at the University of Edinburgh. This is the, well, before starting, I also would like to thank the previous speaker for all such outstanding talks. This is the outline of the presentation. I will start mentioning some geophysical phenomena that involves dispersive shock waves. Then I will describe the anatomy of a dispersive shock wave of KdV type and the dispersive shock fitting method applied to 4 weakly nonlinear water wave models for the description of the macroscopic properties on this board. In this section, I will also take a moment to describe the richness of the Whitham-Boussinesq model that make them suitable for the study of the propagation of surface water waves. Then we will move to the section on fully nonlinear water waves undular bore, and we are following a numerical approach because there is not analytical theory for the description of these waves on this fully nonlinear system. Finally, I will put all these numerical and analytical findings together to establish some results on the applicability for describing oceanic events and on the agreement of the dispersive shock fitting method relative to the fully nonlinear water wave model. Let's start. Dispersive shock waves are everywhere. You can appreciate them in the atmosphere, in the surface of a river, a channel of the ocean, on the ocean, and also in the stratified layers of the ocean. They play an important role in oceanic events, such as coastal tsunami propagation, internal ocean transport, and for the equilibrium of coastal ecosystem. This is an atlas of oceanic internal waves. It's a bit old, but in this workshop we have seen very updated maps of the location of these internal waves. And I am pretty sure that many of these internal waves correspond with internal undular bores. And this and we will have an accurate description of the localization and of the evolution of this bore when we can obtain accurate measurements in the ocean of these waves, and we can understand the different ways of in which these waves can be perturbed when evolved on very complex physical settings, like different stratification in the ocean, or with the different bathymetry that there is in the world, and different depths along the coastal line of the world, and etc. So dispersive shock waves are of interdisciplinary interest, and I am convinced that simpler models that captures with loyalty relevant physical situations can lead us to the discovery of structural properties, and in particular can give us some insights into the long-time evolution of these waves under complex physical settings. Dispersive shock waves is a coherent, unsteady solution that every nonlinear dispersive wave equation has, and they are of multiple scale nature, and they are transient solution. So dispersive shock waves are alive. That's why I wanted to make this video that we generate with real numerical data that we obtained with the Whitham-Boussinesq model that we study on this work. So we can see a dispersive shock wave is an expanding, slowly modulate waveform with a linear wave train at one end and a solitary wave at the other. This structure cannot be appreciated here because the world haven't evolved enough. But this is the anatomy of a dispersive shock wave once it evolves enough. It consists of two edges, the trailing edge and leading edge, propagating with different speeds, with a modulate dispersive wave train between these. The two distinct speeds of propagation correspond to two limits of the modulate periodic wave. When one is you can appreciate that to the right, when the wave number goes to 0, and to the left edges, and in this case, correspond when the amplitude of the modulate periodic wave goes to 0. So this is a typical ondular board solution of the Boussinesq system that I am presenting here. This corresponds with the Whitham-Boussinesq Hamiltonian model, and the initial condition is in the blue line. So currently there exist just two methods to determine analytically the macroscopic properties of the dispersive shock waves. One is the nonlinear wave modulation theory, that if you can set the nonlinear dispersive equation in a set of Riemann invariant form, you can obtain the full ondular board description. But this is only possible for integrable system, and in other cases, Jenna DL and collaborators in 2005, they introduced a method for the description of the macroscopic properties of the boards in these two edges, the solitary limit and the harmonic limit. But to apply this method, some conditions should be satisfied, and you may know them, all of them very well, and I am enumerating here, and we will verify these conditions on the weakly nonlinear system later on. So there are also other conditions that on the Whitham system that should be satisfied, and this condition cannot be verified analytically on at least you can state and solve the modulation equations, but you can verify this condition numerically. And in fact, if you have that your system have a typical ondular board of the KdV type, then you can apply the dispersive shock fitting method. So you can make numeric simulation to see which kind of boards you are getting, and then if the theory will be applicable or not. So if they derive in these two degenerate cases, when the limit goes to, the wave number goes to 0, and then when the amplitude goes to 0, they state the modulation equations in this simpler form, that are valid in these two limits. And from this setting of equation, they could derive the equation for the wave number, and at the trailing edge and at the solitary edge. So these are the the matching equations or general equations that you may find in the literature. And from this, you can compute the macroscopic properties. And we will compute these formulas on this weakly nonlinear system after having verified all the conditions that I mentioned before. So we will obtain these macroscopic properties for the system, standard Boussinesq system, the Boussinesq Hamiltonian system, the full dispersion shallow water equation, and the Whitham-Boussinesq system. All these systems are weakly nonlinear water wave models, and these models have been derived or modeling an inviscid, incompressible, and irrotational fluid, and also assuming that the only volumetric force acting on the fluid is gravity, and the fluid domain has a finite constant depth. And all of them are in the long wave regime that assumes that these two quantities, these adimensional quantities, that relates the wave amplitude, the typical wave amplitude, the typical wavelength, and the mean depth of the fluid domain are small. So I did this slide that I called history bites on the fascinating theory of waterways theory of waterways, and well, everything started with when Euler derived the Euler equation, the water wave equation, from conservation laws and mechanics applied to fluids. And this system of equations are fully nonlinear, a coupled system, and also is a free surface problem. So they are very complex, and not very general thing can be said from this equation. But there have, I will mention some important progress that you can distinguish along the history that happened in this for the development of simpler models to be able to describe some nonlinear and very interesting and shocking behaviors that by the time of Euler, the scientists didn't expect could happen. But then Ursel did some remarkable observation and experiments on a wave propagating in a channel in Edinburgh. And then Boussinesq and KdV derived from the Euler equation some a system of equations that an equation that could describe the evolution of this singular wave that propagates such long distance at a constant depth, and this was the KdV equation, no? And another great progress in this theory was made by Sakharov when he realized that the water wave problem can be restated as a Hamiltonian problem in a Hamiltonian framework, in which the Hamiltonian was the energy of the system. And then recovering this work, Catherine Sulem and Walter Craig introduced the Dirichlet-Neumann operator on this Hamiltonian formulation and reduces one dimension, in one dimension this problem, and this makes possible the derivation, the rigorous derivation of the classical long wave model that existed by that time. So, and then Acevis and Panagiotaros in 2013 introduced the Whitham-Boussinesq model from this Hamiltonian framework using the Whitham heuristics at substituting the dispersive term in the weakly nonlinear expansion of the Dirichlet-Neumann operator. And me, in 2016, in my PhD thesis, I introduced a Whitham-Boussinesq variable model. So this model, Whitham-Boussinesq model, have remarkable properties and that make them suitable for the study of surface wave propagation. they have traveling waves, solitary waves, stop waves. They present the peaking phenomena, the breaking phenomena. They have Hamiltonian structure that is very important to control numerical experiments and at long time behavior, at long time periods. And they can be extendable to 3D waves, to higher order variable depth. And also Carter in 2018 tested the validity of these models on the lab. So doing real experiments in the laboratory. So I will now present each of these weakly nonlinear models. And this slide has a lot of stuff, but I just want you to focus on the system of equations that is in the top of the slide. And if there is a relation on the velocity and the amplitude in the for the solitary waves described by this system. And about the figure, I just want you to verify that it's of KdV type, ondular Born. This is the standard Boussinesq system. This is the Boussinesq Hamiltonian system. In the top, we can see the Hamiltonian, and this Boussinesq Hamiltonian system has been derived from the Hamiltonian formulation of the water wave problem. Also, they have ondular bores of KdV type. And this is the full dispersion shallow water equation. This system has been introduced by Vera Hoare, that gave us a talk last week in 2018. And she took the shallow water of the Boussinesq equation, and substitute the dispersive terms for the full dispersion relation of the Euler equations, like you can appreciate in this slide. And finally, there is this the Whitham-Boussinesq system that has been derived again from the Hamiltonian formulation in this framework. And also they have this kind of KdV ondular bores. So now we will apply the dispersive shock fitting method to these weakly nonlinear water wave models. And first, we have that we check that the non-dispersive limit coincide for all these systems and can be described or be written in diagonal form. And then you can set this system of equation in this in Riemann invariant form, and you get the characteristic velocities. These are all the dispersion relation for each one of the system. This is a plot of the curves of this dispersion relation from the constant background state. And well, here it's clear that the Whitham-Boussinesq system have a better description of the higher modes. Well, once we have all this formula, we can set the matching equation that will give us the equation for the wave number at the harmonic edge and the solitary edge. This is at the harmonic edge, and this is the equation for at the solitary edge. And these are the equations for the Boussinesq derived from the Hamiltonian system B. These are for system C. These are for system D. The last two were for the Whitham-Boussinesq model. So we have here all the system of the matching equations, and the first two can be solved analytically by using the recommended change of variables in the papers of Hofer and Gennady. And the last two can just be solved numerically. So in this table, I am putting together the formulas we got for the velocities and amplitudes of the leading solitary wave, given that we have the relation on the velocity and amplitude for this system. And I am pointing out that the ordinary differential, that the matching equation for system C and D have been solved numerically using a second order Runge-Whitham method. These are some details on the performance of the numerical computations. This has been coded by an extension of the code done by Noel Smail, and we use 2 to the 16 Fourier modes, short time step. And this was the smoothed initial condition we use in this case when we did was with W equal to 1. I am pointing out this because will be important later when we model the Euler equations. So now we will move to the third section of the talk for the description of the water waves ondular bursts. As I say, here we are following the Hamiltonian formulation of the water wave problem. In fact, we started at the beginning of this research trying a different approach because the goal was to integrate numerically these equations, but also in a proper numerical scheme to be able to describe the time with loyalty and for a long time the evolution of these waves. So is a crucial point on the investigation. So we failed at trying to use a curvilinear coordinate system of equation for modeling this system of equation because it was very, very expensive to evolve this equation over such a long period of time. So we moved to the Hamiltonian formulation of the water wave problem in which we could use a pseudo-spectral method to solve this equation. So in this Hamiltonian, as I say, we have the Hamiltonian that corresponds with the energy of the system, and the evolution equation can be set in terms of this Dirichlet-Neumann operator that appears explicitly on the Hamiltonian. But this operator, there is not an explicit expression of this operator for a complex fluid domain. There is just an explicit expression in case of the on the rectangle, but all these researchers have obtained an analytic expansion of this operator, and using a perturbative and variational analysis, they derive the evolution equation. We can derive an evolution equation of the water wave problem at substituting the analytic expansion of this operator and obtain an accurate description of the fluid domains that are changing at each time step. So this code has been coded by Tim Marchand, and we split the linear and nonlinear part of the equation, and we use a split step method. The linear and nonlinear, and then that we solve it at different times, the linear and nonlinear parts, and then we using the second order string splitting step method to advance on time in this way that is given there. So these are the performance of the numerical computations. We could evolve very, very long periods of time to discover very interesting behaviors, and the onset of the modulation instability on this system of equations. So it was just, we just used three terms on the expansion, G0, G1, and G2 for the setting of the evolution equations. We use 2 to the 15 modes, and given of the numerical instability that arise on this system when there is a higher mode, we are using a filter according with the literature of the integration of the system. And also the initial smoothed condition was smoother than one that we use it with the other Whitham-Boussinesq model. And well, we noticed that using W equal to 2 to 5, I think we used 5 was enough for put a description of the board and without killing the trailing edge of the board. So this is now the results. And well, here all the boards behaves pretty well, all of them pretty well, because we are in a low initial condition. And well, we can say the main finding here, that the water waves ondular boards are a bit behind of the other Boussinesq boards, and that the trailing edge has very well predicted, that you can see on the blue line, and that the amplitudes on the Boussinesq system that are at the top are lower than the amplitudes of the Whitham-Boussinesq system. And well, also we noticed that the ondular board, the water waves ondular boards took an unrealistic amount of time to reach a steady state, and we couldn't, in order to measure the macroscopic properties, the amplitude at this steady state, we needed to use an extrapolation of the evolved board and to make possible to have a prediction on the amplitude and velocity. And so these are the results on the velocities of the leading edge. We see that there is a very good agreement on the Whitham-Boussinesq system, and below the initial jump of 0.1, the agreement is okay for all the system. And well, for these are the results we got for the amplitudes of the leading solitary wave. We see that the ondular board amplitude lies on between the Boussinesq and the Whitham system, but the Whitham system are have a better agreement when they are far from the modulation instability. And I am not too much time, but I'm just 2-3 minutes, and that's why one good point about studying this Whitham-Boussinesq system is that we have a better, as I said, the description of the higher modes. So in this system, we were able to study the modulation instability, and this is what I am presenting here. This is for system C, that has a modulation instability very earlier, for initial jump of 0.3, And this is for the system Whitham-Boussinesq system. We cannot see the details because I didn't put the caption of the figure, but this is the instability that we observe at 0.32. The board develops a modulation instability, and for the ondular boards it takes longer and to develop this modulation instability, and also at higher initial jumps. So this is the summary of the presentation that I presented today. And well, I just want to mention that I am working on this research project with Tim Marchand and Noel Smile. We are now studying the Whitham-Boussinesq system, but with surface tension. And in this case, we have resonant ondular boards. And in this case, the fitting method cannot be applied. And also with Panayotis-Panayotaros, I am working on modeling and develop a good model for the description of the propagation of water waves on an inclined walls domain. And thank you very much for your attention. This is all.
Thank you very much, Rosa, for your talk. So I think we're running a bit over time. There is time for one very short question. Is there any question? I'll probably quickly ask if there is no question. How do you choose the initial condition to observe this modulational instability?
Well, we should take in consideration the regime that we are describing. These are the long wave regime, and so the amplitude should be low, small, to be able to, for the good accurate description of these models on these waves too. So, and then we just looking at the onset of the modulation instability to determine the higher amplitude that we could obtain. But of course, we were interested in modeling dispersive shock waves. So we went. The only initial condition we wanted was the step condition, and to see how was the dispersive resolution of this initial step condition at different amplitudes.
Thank you very much. So I think more questions, we can postpone further questions to the break. So I'm sure Rosa will be happy to answer questions in a breakout room.